Hey, hi everyone. So welcome to Massive for F again, which is the Advanced Engineering Mathematics for ME. So for this video, I will discuss the root finding algorithms for solving nonlinear equations. So let's briefly discuss the intended learning outcomes, which are the following. So to solve the real roots of an equation using open interval and closed interval methods, and then we want to compare the two different methods or the general two methods or the two general approaches in finding the roots. And then we want to also find a way to verify the solution of our methods. Okay, so the outline here will be some introductory concepts before we deal with the closed interval and the open interval methods. Okay, so for the closed interval, there are two methods that we will discuss. For the open interval, we have three methods that we will discuss. All right, so let's get ahead and let's discuss how do we find the solution of, let's say, an example of your function. So let's say you have a given function that looks like this. So how do you solve this on the board? Without using your calculators, how can you solve this? So actually, it could be possible to solve this, but you will recognize already that this cannot be represented in its explicit form, meaning you cannot have x is equal to some function that only has constants, in other words. So therefore, this equation cannot be solved through elementary analytic methods. So now we could solve this using different methods in numerical methods, and we all know that we could utilize our calculator to solve this. We could just utilize the shift solve, or again, using numerical methods, which are the root finding algorithms. So many engineering analysis require determination of a function or the solution of a given function that is usually in implicit form. Okay, so how do we find the roots of this function? So there are different roots of the function. We have real and distinct roots. So real lang siya, distinct, different roots. It could be real and repeating. So it could be repeating. We have two ones, two twos, two threes, and so on. It could be a complex number or a complex conjugate. So one complex number is a complex conjugate that represents, actually they represent two solutions, or a mixture of these three types of roots or solutions. So let's say we consider some fourth order polynomial function. So the graph of this, let's say an arbitrary polynomial function, which is x raised to the fourth power plus x 6x cubed plus 7x squared minus 6x minus 8 is equal to 0. If we graph this function, implicitly, the representation of this will be this line. So we have three extremas. We have how many roots? So a polynomial should have four roots, diba? It could be a combination of real, distinct, real and repeating, or complex conjugates. So as we can see here, we have four solutions in our function. So this is basically their solutions. The intersections with the x-axis will be the solution of your function, which, as you can see here, f of x is equal to 0. So when f of x is equal to 0, we have a solution of x's here. That is why f of x is equal to 0, or the x-axis, or the intersection of the function with x-axis will be your solution. Okay? So for other functions, it could be that we have a repeating, so it could be a double root here, and we have two distinct representation of our solution. And then we have, let's say, no solution. Sometimes we do not have an intersection with the f of x equal to 0, or this x-axis. And usually our treatment with that is that it has or it only has a complex root with regards to polynomials. No? Now, again, no, knowing that our equation or our algebraic equation would be a polynomial function or a transcendental function, okay, how do we solve them in general? No? So for polynomial functions, if it is only a second order polynomial function or quadratic equation or a quadratic function, you can just utilize factoring, usually completing the square, no? Or the quadratic formula. But for higher order functions, for cubic, no, for x cubed, x to the fourth power, no, we cannot, no, usually we have still analytic solution similar to this, but it will be cumbersome. The formula will be very complicated, and the practical way to solving higher order polynomial functions will be the numerical methods. Okay, so now, again, for transcendental functions, for direct methods, it will be limited. No, kapag may logarithmic, exponential, it will be complicated to solve this analytically. So we usually utilize numerical methods. And again, the graphical representation of the root or the solution will be its intersection with this x-axis line. Okay? So now, we have the incremental search method to determine at which, no? So since we do not know the solution of our function, we could do the trial and error, no? So para magta-try tayo ng values, we'll try different values to our function, and then we might see some intuition on where the root lies. Okay, sige, let's try doing this. Let's say we have a given function. We want to find the interval on which the root is found. Ano? So, we have a polynomial function. We want to just figure out where where the roots will be found. So we could utilize our calculators for exactly just that. And how do we do that? No? So I will teach you a calculator technique to do just that. So we have shift and then mode. Sorry, not shift mode, but we have mode and then table, so 7. And then just input the function here. So we have x cubed, so alpha x cubed. And then we have plus 10x, alpha 10x squared, plus 14x, and then minus 16, and then equals. So the interval at which we will find the solution, let's just find the solution in between -9 and +9. So I'll just put here -9, and then +9 for the interval, and then the stepwise, no? So at which points or at which interval are we looking for, no? So let's just divide this -9 and 9 by one step, no? So let's just input here 1, and then as we could see here, we could have a table of the x and the f of x, no, of our functions. As we could see here, ayan, no? So for starting from -9, so from -9, actually we have a root, no? We have already found the root, which is -8. Okay, so if f of x is 0, that is the root. So the root here, no, already we could write here down. Sorry, so the root here is -8. No? So first solution is -8. Okay, for the other solution, we have another solution. Okay, so we have here, no, as you can see here, there is a change in sign, no, from 5 to -12. And if you realize this, no, going back to this graph, our function of x here, no, this is negative, right? If the height is going down, the f of x is negative. And if the height is going up, no, so with respect to the x-axis, it should be positive. So if there is a change in sign in f of x, then there will lie our solution or our root. So therefore, with regards to our calculated table, the solution lies in between this -3 and -2. So one of the solution here is in between -3 and -2. or let's just make this an exact, or anyways, it's the same, no? And then, do we have another change of sign here? Let's see. So again, we have another change of sign. So from negative to positive f of x, meaning there is a transition from the negative height to the positive height. Therefore, the solution lies between 0 and 1. So x sub 3, we have 0 and 1. So let's see this now. Let's just see this. So as you can see here, if we graph this function, we have the solution. So we have already negative 8. And then somewhere in between negative 2 and negative 3 lies another solution, no? Which is this. And then somewhere between 0, so this is 0 and this is, let's say, this 1, we have another solution. So we could utilize this incremental search method. So basically, we're just trying different values of x and then calculating the f of x to find the f of x is equal to 0. So if the sign changes, again, there will be, or there will the root will lie in between that interval. So what do you think will be the limitations of this root finding algorithm when we utilize this trial and error? No? So this is basically trial and error. No? So we will discuss that later. Okay, so for letter B, I will not show the tabulation here, but I will just show you the graph. So for this second one, you can see here we have multiple solutions. No? So we have this solution, and then we have infinite solutions. No? As we can see, the function is periodic. We might have, no, actually we do not know if this is infinite, but we might have an infinite solution of x. Okay, so we can find these solutions using numerical methods. So again, what is the problem with this incremental search method? So the problem here is, let's say the interval or the increment length is too small, then as you can see, no, the tabulation will be so many. Kapag marami kayong difference, no, pag nilitan niyo yung search, no, the computation will be much larger, the tabulation will be much larger. If the increment length will be larger, so the space in between will be large, some of the roots might be missed. So pwedeng lumampas, no, or there might be some cases that the roots will not lie, no, in between that large interval. Okay. Okay, so let's discuss here now, no. So knowing that we have these two things, so we have the f of x equal to 0, the changing of signs, we can now move on with that in mind, the two methods or the two general methods in solving nonlinear algebraic equations. So for bracketing methods or the closed interval methods, usually we have two, no, initial guesses that are the interval in between. So we have to know in between ano yung x's natin doon. And then in between these two, no, in these two interval, we can find the solution. So the problem with that is it will converge slowly, but it will always, no, most of the time it will work. And then for open methods, usually we do not have two, no, but we only have one initial guess, and then it will converge to that solution. The problem with all open methods is that it might diverge or it might oscillate depending on the method you're using and the function that you're trying to solve. Okay, so a brief representation of bracketing methods and open methods. So for A, we have this given solution here. Sorry, we know that this is the solution, and then we could find the solution in between xu and xl by internal halving. We have this bisection method, and then for number 2, we have the open method. This might be the Newton-Raphson method, since this is what do you call this? A tangent line. Okay, we will discuss this later. Okay, again, we have bisection method and regular fallacy for bracketing. For open methods, we have fixed point and Newton-Raphson, and then secant. Okay, so for bisection method, this is also called the refinement of the incremental search method, which is also called the internal halving. This is extremely simple and safe, but it is time consuming, for most of the cases. So let's say you have a given function, no? And you can continue to have your intervals until you arrive at a given point. So let's say you have a bracket, no? Let's say this is your two brackets. You keep this in half, and then this will be your new solution, and then you will have this again. So you keep on having until you get the final solution, which, and as you can see here, it will converge to this true solution. Okay, so how do we do this? So the formal representation of this, okay, I will not discuss this now so that it won't be hard for you. I will just give you the easy way to implement this using tabulation method. Although this algorithm or this process is, or this could be utilized for implementation on some programming languages if you want to program your own numerical method calculator. Yeah, let's just discuss this tabulation here. So let's say you have a given function. Okay, you have a given function here. You want to find the root of your function. Now you want to find this x. So to find this x here, you have to first figure out where does our solution lie. So we have to utilize the incremental search method first. So using the incremental search method, we will try again on doing this. So again, mode 7, and then input the function. Okay, and then minus x. And then tabulate this. So we will start from the negative value, no, in general, -9 to +9 all the time. And then the step will be 1. So we will try to find where does the root lie, or where does the solution lie. So we're trying to find here at which point of x interval will the sign of f of x change. So as you can see here, the sign changes from 0 to 1. Therefore, the root lies in between 0 and 1. So our x lower will be the lower, now the left end of our interval. So the lower now, meaning it will be 0, using our incremental search. So this is 0, this is 1. Okay, so 0 and 1. So the iteration is the first iteration. So we have the first iteration. And then what should we do? So we have these two initial guesses, the x lower and x upper. And then we want to find the half of this xl and xq. So we want to find the midpoint basically. So we have 0. So this will be 0 plus 1 over 2. This will be equal to, so 1/2, which is equal to 0.5. Okay? And then you can compute for the percentage relative error or approximate error later on if we have a previous. So since we do not have yet a previous, we don't need to write this yet. So this should be blank. And then after that, we have the second iteration. And there are a lot of things to do here na nakalimutan talaga pala natin. So we have to also figure out pala what is the sign of your f of x l. Ano yung sign f of x l? Ano yung sign f of x u? So the sign of f of x l is, so the lower now, so 0 is positive. So if this is positive, then this one is negative. Ayan. So what should we do here after that? So again, in internal having, we have a given function. We have a given function. Let's say this is positive. F of x is positive here. F of x is negative here. Therefore, our root lies in between these two. So if we do the internal halving, let's say we have this two, no? We have this half here. So that our new solution here will be this length here. Okay. So we should change here. If our f of x here is negative, then therefore we have to change this x here. So basically, we have to also find the sign, no, the sign of this f of xm. So f of xm, ano yung sign niya? Negative ba or positive? So is it negative? Is it positive? So we have to substitute this f of xm to our function. So we have alpha a raised to negative x, sorry, alpha negative x, and then minus alpha x, and then alpha equal to 0. Sorry, not equal to 0 na pala. I-calculate nga pala natin yung 0.5. So, calculate 0.5. Okay, so we have 0.106. So, if this is positive, then we have to replace the positive. So, this will be replaced since this is positive. So, this will become 0.5, and then this will still be 1. So, retain lang yung 1. Okay, so ganun lang yun, no? This will become positive. So since it's positive, we replace the positive. And then after that, we want to find the xm. Okay, so I will just continue tabulating this. So the midpoint is 0. This is equal to 0.75. Okay, so this will be what sign? So we want to figure out what sign is this. So again, use the calculate function, replace the x with 0.75. So this will be equal to negative. So if this is negative, then you will replace now the negative. Xu is negative, or f of xu is negative. So we have 0.75 here, and then retain the 0.5. So this will continue on and on and on. Okay, and then continue to find the half of this. So 0.5 plus 0.75 over 2. Over 2. So the answer should be 0.625. Okay, guys, no need to write this one in your worksheets or in our exercises. And then I will write this down later, guys. And then move on to the next one. So what is the sign of this? So if this is positive or negative, let's figure this out. So calc again, 0.625. So this will be negative. So negative, okay, so negative dito. So 0.625. So we will replace the negative again. So we have 0.625. And then we have here 0.5. Okay. And then moving on, for this, we have 0.5 plus 0.625 over 2. So keep halving, no? So the answer should be, calc, we have here 0.5 plus 0.625, and then divide by 2. So again, we have a negative value. So we need to replace, sorry. What did I do? So we have to find first half. Okay, it is midnight here, no? I think I'm feeling sleepy already. 0.625 over 2. Yeah. Okay, so we have sorry, what did I do wrong? Sorry, not negative. Pinito pala yung minus. So the answer is 0.5625. 565. Calculate this again. Okay, so there is a repetitive nature to this topics, no? So this is positive, no? So we're looking for the sign here, so positive. So we will replace this positive 0.5625. And then retain 0.625 for the fifth iteration. And then again find the half. So we have 0.5625 plus 0.625 over 2. So the answer should be 0.59375. 59375. And then keep halving, no? Again, so substitute the function again. So 0.59375. So the answer is negative. So if this is negative, we will replace the negative here. So we have 59375 and then 0.5625. So this will be the sixth iteration. And then the last approximation here will be when we divide. Again, we find the midpoint of this two. So 565 plus 0.59375 over 2. Ayan. So 58, 0.578, 1 to 5. Okay. So now let's find the approximate error or the relative approximate error. We will just solve this. I'll just do this fast now. So we have d minus c over alpha d and then multiplied by 100. Okay, so d here is our, no? So d is the present, c is the previous. So for this first one, we have the present is 0.75, the previous is 0.5. So the answer is 33.3%. Okay, for the next one, we have 0.625 and then 0.75. So the answer is, what did I do? Okay, so 20%. Okay, tama naman pala. And then next one, we have 0.5625 and then 0.65. Okay, negative 11. So absolute value, guys. So we have 11.11%. And then move on. We have 0.59375 and 0.5625. So the next one, we have 5.261. 5.2631%. And then another one, 578.135. So the present and then the previous 0.59375. The answer should be 2.7027. 2.7027%. Yan. So this should be your final answer. So it should be also, this should be your final approximation of the solution at this approximate error. So depending on the context, so sometimes the problem will ask you stop approximating when it reaches this certain approximate relative error, and we will discuss this in our succeeding examples. Okay, now so the representation of the solution, if you can graph this, will be this, no? Okay, so it is that simple. So the solution is somewhere in between 0.4 and 0.6, which is relatively correct, as you can see here. Okay, so let's have another example, and let's try doing this in a quicker way. So to find the root of this function, again, we want to set up our table. We have the iteration counter. Iteration counter, we have the XL, okay, we have the XU, and then we have the midpoint, XM, and then lastly, we have the approximate, the relative approximate error in absolute value. So for the first iteration, the XL will be 1, the XU will be 2, and then let's find the XM. So the XM here will be the midpoint here, so we have 1.5. Okay, so we do not have yet the previous value, so let's continue. Okay, so let's substitute the values here. So guys, to make things quicker, just write the function in your calculator and then substitute the value respectively for each of the values. So we have here, actually we have to first determine the signs of your f of xl, f of xu, and f of xm. Okay, anyways, let's substitute the values here. Minus 10. So let's find the sign of f of xl. So let's substitute 1. So if we substitute 1, the sign of xl or f of xl actually, no, is negative. So I won't write f of xl anymore, no. So I will just say that this is negative. It's f of xl is negative. And then therefore 2, it is positive. So let's see if f of xm is positive or negative. So substitute 1.5. So the answer is positive. So therefore, if this is positive, then we will replace the positive So we have 1.5 here, and then retain the this one, and then second iteration, and then divide this or find the midpoint. So we have 1.125. I won't utilize the calculator. And then you can calculate also the relative approximate error. So for the relative approximate error, just utilize this, guys, ha? So we have alpha D minus alpha C over alpha D, and then multiply by 100. Okay? And then, so I'll just write this down here. So D minus C over D times 100, where D is the present, the C is the previous. Okay? So this is for the relative approximate error. So substituting the value 1.125 and 1.5. So we have 33.3%. So 33.3% or 33.33%. And then for the third iteration, we want to know the sign. So we want to know the sign. So substitute 1.125. So the sign of 1.125 is negative. So we will replace now the negative here. So we have 1.125, and then retain this 1.5. So we have 1.5 here. Find the midpoint again. So I think I cannot do this mentally anymore. So I guess let's create another automation. So we have a plus b, and then over 2. Okay, so we have here we have 1.125 and then 1.5. So the midpoint of the two, we have 1.135. All right, 1.3125. Okay, and then substitute the value to our function. Sorry, not that one. This one. So substitute this. 125. So this, since this is negative, then we want to repeat this for the XL. And then let's find the relative approximate error. So for relative approximate error, just browse through your previous calculations. So previous, present muna, no, 1.3125, and then the previous is 1.125. So the answer should be 14.285, right? 14.285. Okay, 14.285, right? 57. Sige, 14 significant figures na lang, 2.8, 29 na lang, no? And then, continue. So, replace this one again. And then, find the midpoint again. So, it will be repetitive, no? It might be boring to do this for most of you, but it is interesting that we have a way to solve the roots using a different method. Okay, so the answer should be 1.40625. Okay, so let's figure out what is the sign of the function. So calc 1.40625. So it is positive. So we will now replace this. Since this is positive, we have 1.40625. Okay, since it's positive, and then let's find the approximate error. Sorry, not that one. This one, so we have 1.40625, and then 1.3125. Yeah. So the answer should be 6.66%. So probably we have only one step to finish, no? This calculation. Okay. Yeah. Let's copy paste this one, and then for the new iteration, and then internal half this again. So find the midpoint again of that. So calc 1.3125, and then 1.40625. So the midpoint will be 1.35, 1.359. 4. No? So I will just utilize 4 significant figures, guys. But if you want to complete this, it's okay. No? The true value, the most that your calculator can give you, no? The most precision, you want to do that, then yeah. But for me, I will just utilize 4 significant figures. So let's find the approximate error. the approximate error will be 1.3594 and 1, actually I did not utilize here. Anyways, okay lang yan. I did not utilize for significant figures in this fourth iteration. But anyways, okay na yan. So negative 3.44. So we have 3.446%. So therefore, this is less than or equal to 5.0%. Therefore, we will terminate this. So the solution that we're trying to find, so our x or approximate solution, we will call this x tilde, that is equal to 1.3594. Okay? That's it. So, let's move on to the different pitfalls of the bisection method, meaning this is not foolproof. No, we will encounter problems with bisection method. So there are imperfections in this method. So one of the imperfections of that method is that when we have more than one root in between our, so as you can see here, we have, let's say this is our interval in between these two. So if we have more than one root, as you can see here, there might be a problem with the root finding. Okay, if we get a half, no, sometimes it will have two. We will encounter the problem here. No? We will have two negative signs. No? And then sometimes if we have two roots here with a very small difference in between them, so we do not find this difference in the signs, no? Since the f of x here will be negative, the f of x here will also be negative, f of x here will be positive. So sometimes if our incremental search is too large, we might not get this f of x here. So we might not find the roots, no? Also for double roots, we will not have a different signs, as we can see here. So this will be positive f of x, no? And also this one will be a positive f of x. So it should be different signs, no? And then if we have, let's say, an even number of roots, okay, and we also cannot find the complex roots. We can only find the real roots of our function. Okay, and also the singularity points. So let's say one example of that is 1 over x. So let's say you want to find the solution of 1 over x equal to 0. No? So what is the solution of that? It could be positive infinity or negative infinity, depending on your perspective. Okay? But using numerical methods, it might be different, no? The solution might, it might approach to 0, no?